I work at LinkedIn, and I've been talking about scaling Hadoop applications. A little bit about me. I was there at Yahoo when Hadoop was born. So while many people may claim to be father and mother of Hadoop, I claim to be one of the Hadoop midwives. So over the last 5 years, I built the grid solutions team here, helping the new migrants, thousands of migrants to Hadoop, and helping them scale their applications. Okay. So what we will be talking about today is scalability of applications, in particular Hadoop applications. Some of the common causes that I have observed over the years of sublinear scalability of typical Hadoop applications, and we'll end with best practices. So why is scalability important? Why do we even need to think about scalability? Forget about Hadoop, but even in other aspects, right? We have been taught from our childhood that we need to deal gracefully with failure. In fact, Hadoop does a very good job at that, handles hardware failures and keeps on going, right? But we need to really think about what if our system, our product, our application becomes successful, has millions of users overnight, and now without rewriting the whole code, we got to scale to these to handle all these number of users. This picture is from 2007 from one of the proposals, research proposals for data-rich computing, and you can basically see that the data that is available to us today, machine-generated, human-generated, all these data that we want to analyze for analyzing patterns, gaining insights into it, is exploding. Now nobody basically blinks when somebody says, I have a few petabytes in my backend, right? So obviously, all the applications that we build today, as well as we'll keep on building tomorrow, is going to be based on this data. We need to scale to handle this data, and that's where Hadoop really comes into the picture. Hadoop really shines into that because it simplifies building parallel applications. Building scalable parallel applications is hard, and most of the details of parallelization, most of the messy details of parallelization are handled very well by Hadoop. All that the Hadoop programmer needs to do is specify a few sequential computations. What do you do when you get a key value from input? What do you output there? And the second sequential computation is basically when you get a key and a group of values, what do you need to do with that? Both are sequential computations that you feed into Hadoop, and Hadoop just parallelizes it over thousands of machines, or whatever number of machines that you have available, right? So while writing a Hadoop application, people typically tend to forget that they are actually writing an application which is going to run on thousands of machines, hundreds of machines, okay? And that in the end comes and bites you, okay? So when you are thinking about building Hadoop applications, essentially you have to think that you are building these massively parallel applications, okay? So we need to think about scalability of parallel applications in general, okay? So the scalability of parallel programs can be defined in two ways, okay? When you have additional hardware resources available, when you are, let's say, building an application on a single machine, now you have hundreds of machines available. So you could be doing one of the two things. If your data size is fixed, you get a fixed data size, then you would like to speed up the application processing this fixed data size, okay? Or if you have one node that can process maybe a few hundred megabytes per second or a few tens of megabytes per second, then if you have 100 nodes, you would like to scale it in proportion to the hardware resources that you have available, right? Both are similar definition, but slightly different in context, okay? So when you get the speed up to be proportional to the amount of, or the number of hardware resources that you have available, that is what is called as the linear scalability, okay? So the two aspects, the two definitions of scalability here essentially corresponds to the two goals of scalability. One is to reduce latency, which means minimizing the program execution time for the amount of data that you have. And the second one is to maximize data processed per unit time, okay? So these are the two goals of scalability. So when you are thinking about scalability of parallel applications, all that you need to know, and this has served me very well over the last 5 years, are essentially these three equations, okay? And hope you like the picture there because I don't have much to say on this slide. So the first equation there is called Amdahl's law. Okay, this is named after Gene Amdahl, who was at IBM at that time, who proposed this law at I think in 1967. So what this thing says is that if you have a parallel application in which some amount of work, some fraction of work has to be done sequentially, and that fraction of work is, let's say, alpha, then you really cannot scale the entire application to beyond 1 divided by alpha. So if you have an application where 5% of the work has to be done sequentially, then however many machines you have available, you will never be able to get a speed of more than 20 machines. That's what I'm talking, right? But the parallel computation model inherent in this equation is actually fairly simple. It basically has two phases. One that has to be done sequentially, and the second one that has to be done in parallel. Okay, and obviously not a lot of parallel applications just have this simple computation model. Typically, what a parallel application has is multiple phases in which each phase can be scaled up to a different or can be executed on a different number of machines. Okay, so these are the multiple phases of computation. So if a computation C is split into multiple phases, C1 to Cn, and if each of these partial computation C can be speeded up by a factor of S, say, then the Amdahl's law can be stated as this equation. And if it is getting too theoretical, too mathy, just think about this. This is the MapReduce workflow. In the MapReduce workflow, you basically have a single job client which is executing maybe on your gateway machine or something outside the cluster. That submits a startup task. That startup task executes on some machine in the cluster, but again it's single threaded or running on a single task. Then you have a bunch of map tasks which can run or which are typically run in parallel. These map tasks produce certain output. All that output gets partitioned, sorted, gets to the reducers. Reducers do these computations on this group. Again, after the reducers are done, there is a cleanup task which does some cleanup, fortunately. And then after the cleanup task is done, the control comes back to the job plan. So now you can see that there are 3 or 4 sequential bottlenecks right there. The job client is doing its work sequentially, the startup task, the cleanup task, and back to the job client. And then the second is typically the width of parallelism in the map phase and the reduce phase. Both are different. Okay, so this is where this whole multi-phase computation equation comes into picture. The second equation that you would do well to remember is something called Little's law. Okay, from an economist in MIT called John Litt. So what this law says is that the total number of occupants in the system is essentially a multiplication of their arrival rate and the amount of time that they spend within the system. Okay, so lambda is the arrival rate and W is the amount of time they spend in the system. We have seen the examples of this in practice. If let's say a university is admitting 1,000 students a year, and on an average a student spends 4 years there, then at any time in the university you will hope to find 4,000 students, right? That's basically the simple thing. Now, when thinking about Hadoop clusters, especially in capacity planning for the Hadoop applications, you need to revert this law a little bit. I mean, just turn it on its head, which is, we know the maximum total number of occupants in the system, which are the maximum number of tasks which are executing concurrently on all the nodes. Okay. Now, if we know how much on an average each task spends doing its work, okay, then you can actually reason about how many incoming task rates, what is the incoming task rate that you can support on this cluster, right? So Little's law gives us a guidance into that. The third equation is the message cost model. And this typically happens when one machine is communicating with another machine. Okay? You are sending some message. Now, the time that it takes to send that message and maybe respond to that is essentially has two components to it. One is the fixed cost, which is typically what we refer to as latency, and the second one is a per byte cost or per unit of work cost, which is what we refer to as MAT. Okay? So let's take a bit of concrete example here. Let's say we have a gigabit Ethernet link, Everything being fine, we'll expect to get around 300 microsecond latency for a TCP message transmitted over TCP on this gigabit internet, and the total payload bandwidth that you expect to get is around 100 megabytes per second. Okay, so you have to send 1 megabyte of data from one machine to another. You split that into 100 messages of, let's say, 10 kilobytes each. It's going to take you 40 milliseconds. But if you can wait and you can chunk those messages into, let's say, 10 messages of 100 kilobytes each, then you get a significantly lower time to send that 1 megabyte of data, right? Alright. So one of the common mistakes in reasoning about the message latency model is to assume that these constants, alpha and beta, are actually constant. Because if you look at, let's say, a reduced task wants to fetch output of a map task which has just finished, which it knows that it has just finished. It goes to the task tracker. It says, hey, I heard that the map task so and so has finished. Give me its output that is intended for me. So now the task tracker, which is executing on the source machine, it's obviously executing concurrently with all these other tasks that are executing on that machine. So in order to get the CPU's attention on that task tracker, it needs to do a context switch. And obviously the amount of time that the time quantum that the task tracker is going to get is going to be inversely proportional to the total number of processes, tasks in general that are running there. Okay, so it depends that message latency for the responder to actually respond to your message is going to depend on how many tasks are actually running. Okay, so that's alpha is never constant pattern. You need to figure that out. The second thing obviously is to assume, second mistake is to assume that beta is constant, right? And when multiple messages are going across these two machines, obviously there will be network congestion. First of all, the source machine's bandwidth is going to get divided among these multiple connections to the destination machine. So beta is dependent on the amount of simultaneous connections that the machine receives. Okay. Alright. So with those three equations as our tools, let's see what are the common causes of sublinear scalability in Hadoop applications. Alright. So the first one is sequential bottleneck. Right. In Hadoop applications, what I have seen is most of the time when people submit a job, they either forget or they do not know how many reduced tasks this computation should have, this application should have. Okay? Hadoop does not help you there, unfortunately, because Hadoop has no way of guessing how many reduced tasks should the application be running. Okay? So by default, it assumes that it's going to have only a single reduced task. Now what is going to happen is all your map output is going to get partitioned and sorted, and all of that is going to come to your single reduced task, and then that single reduced task essentially becomes a sequential bottleneck for your computation. If you are using Pig, you could basically override this by specifying a parallel directive on the statement that invokes that causes Pig to generate a reduced task. Okay? So the parallel 10, if you specify, for example, for a join statement, then it will have 10 reduced tasks, right? So apparently Pig now has a sort of clever way to reduce the number of reduced tasks for each of its applications that it generates. Right? But Pig script essentially generates multiple Hadoop MapReduce jobs. Okay, so initially the default for parallel was 1, and when we ask people to specify a parallel directive for each of their reduce and inducing statements, they would basically say, I don't, it's too painful to edit that Pig script now and add those parallel tasks. So the Pig developers, being very friendly to their users, essentially introduced something called a default parallel, which basically means that all the MapReduce jobs that are generated as part of that Pig script will have the same number of reducers. But then take a look at our message cost latency model, right? The number of messages that go between these maps and reducers are going to be significantly affecting the time that it takes to shuffle the intermediate output, right? And the size of the message is what really matters. You cannot really decide, you cannot really say that no matter what the size my intermediate output is going to take, I'm going to have the same default parallelism. Okay? So you need to think about what parallelism you want in your reduced tasks. The second most important cause of scalability or sublinear scalability that I have seen is load imbalance. Okay? Load imbalance is caused by uneven partitioning of code. Now, if you have some map task which is going to process 100 megabytes versus another map task which is going to process only 2 megabytes, you would expect to see the 2 megabyte task to finish faster, and then all the reducers are going to then wait on that 100 megabyte task to finish. Okay, so that's uneven partition. Okay. Even if you, in your application, you partition your input so nicely that every map task gets exactly equal amount of work to do, your hardware might be heterogeneous. You might have some nodes which were you bought today, you bought faster nodes tomorrow, and now you have a heterogeneous cluster running this application, and now that is the cluster-induced load imbalance. Okay, even if you bought all the nodes at the same time, some nodes got filled up earlier, some nodes were sort of have empty disks, and then now you have load imbalance in data throughput from those disks, right? So the load imbalance could be in the application as well as in the cluster. You can't really prevent that. So one of the ways to deal with this kind of load imbalance, both in case of the hardware-induced load imbalance as well as the application load imbalance, is to over-partition your input. Okay. So if you have, let's say, n computational resources, n machines, you over-partition your application or your application input into, let's say, m tasks or m map inputs, so that m is much larger than the amount of machines, the amount of task slots you have available, maybe about 5 to 10 times larger. Now, Hadoop has a very nice adaptive scheduler, which basically means the task assignment does not happen statically from the job tracker to task trackers, but whenever a task tracker has free slots, it goes to the job tracker and says, hey, I have spare capacity, just give me a task to work on. Okay, so that works very nice. And when you have over partitioned your application on the map side, then it basically becomes most of the time what will happen is that the amount of work which is done by each of these task slots will sort of average out. Okay, so then the load imbalance essentially gets to zero. All right. The third sublinear scalability problem is in critical paths. Now, there is one, and the critical path is basically defined as when you divide your computation, or when you sort of model your parallel computation into a directed acyclic graph, then from the beginning node to the end node, whatever is the maximum path length between the beginning node and the end node, that's your critical path. The case or the place where this thing comes into picture in Hadoop is when you have perfectly load balanced application or perfectly load balanced cluster. Some map task essentially takes longer for some reason, maybe it's doing more computation, and then all reduced tasks are waiting. Okay, or some shuffle gets stuck somewhere, and then that particular reduce is waiting. And unless all the reducers are done, your application is not complete. So that basically causes a critical path. So one of the ways to handle this is for tasks which take longer than they are expected to do, you typically enable speculative execution so that multiple attempts for the same task are launched simultaneously on multiple resources if resources are available, and then whichever finishes earlier is taken up, and so that means and the other outputs are discarded. So that means now your critical paths, the long tails that you see in your computations, are reduced to none. Okay. If you are doing, or if you have a graph which basically where each node represents a MapReduce job, where each MapReduce job output goes to another one, try to avoid depending on the last job's output, or actually if you are doing some work there which is unnecessary, which can be done out of band, just postpone it to do this asynchronously somewhere else, or maybe split it into a different data pipeline, right? So that way you can avoid the critical path. The third thing to note, or the fourth thing to note, is basically that you are writing a parallel algorithm, or you are coding a parallel algorithm, right? A parallel algorithm, when we have a sequential algorithm and we convert that to run in parallel, obviously there are going to be more overheads. The parallel algorithms in general perform more computations than the equivalent sequential algorithm. That's the fact of life. Otherwise, if we had a parallel algorithm which was more efficient, then the corresponding sequential algorithm will take the parallel algorithm and emulate it sequentially, right? So this is the fact of life. The parallel algorithm is almost always more computationally intensive as in number of computations than the sequential. So we can't really do much about that. But if you look at most of the Hadoop applications, what they're doing is, or many of the applications that I used to work with, is what they're doing is exploring some sort of a solution space for maximizing certain quantity, right? Typical optimization problem. And now you basically have to traverse this solution space in some way, and since each task is executing independently, they basically have to fetch the next unit of work to work on and go ahead from there. So now you got to check whether this unit of work has already been performed by some task somewhere. Okay, so for that you need a central coordinator. For example, in crawling, you got to have a central coordinator to see whether this URL was already crawled or not by some other task, right? So you need this centralized coordinator to share partial results. Now, if these partial results are small enough, you can share them using a non-materialized, unmaterialized, a small replicated key value store, so that you can just immediately make a call and see if this work has already been done before. If it has not been done, then the task takes up that work and performs it. Okay. Since Hadoop allows you to scale out, most of the synchronization issues in like thread synchronization, etc., those are gone. Right? You basically write tasks which execute completely independently of each other. Okay? But there is one huge synchronization stage, unfortunately, that's still left in Hadoop, which is the shuffle from the map. The map output has to go to the reduce input. So that's one big synchronization step. That's the fortunate part, that there is only one synchronization step. What is unfortunate is that this synchronization step actually involves the slowest of the system components, which are disks and networks. Okay? So the map output has to go onto the disk, so that even if the map goes away, somebody will be able to fetch it. And then it has to get transferred over the network to the reduce task. Okay? So shuffle is often the most critical component that you need to focus on when you are trying to scale your application. Okay? If you can write your algorithm in such a way so that you can do everything on the map side and have no shuffle at all, no reduce stage at all, that's the best, right? So you can just, if you can eliminate the reduce stage, that's the best. If you cannot, then at least try to make the shuffle stage efficient by doing partial local aggregation on the map side using compilers. Okay? If you somehow the compilers cannot be used, then at least try to compress the intermediate output. Your CPUs will, or your network will thank you for it. Okay? Because most of the time, the output, the map output that I have seen compresses very well. 3 to 4. I mean, I've probably worked with thousands of applications here at Yahoo for the last 5 years. Typical compressions that we typically get is between 5 to 10 times. Okay? So basically, you spend some CPU trying to compress, but you save in the disk storage cost, as in time to write that map output onto the disk, as well as on the network transfer cost. Okay? The last part that I have, which causes sublinear scalability, is too small tasks. Now we saw the message cost model, right? There is some fixed cost associated with transferring a message, and then there is a per byte cost. That cost model applies very well to the task execution as well. The task tracker has to go to the job tracker when it has a slot free. It has to go to the job tracker and says, hey, I'm free, give me a task. Now the job tracker is a single server. It has to basically choose from among the thousands of tasks that it has pending, it has to choose the right task. Now for that it has to do some local greedy optimization, right? So it has to do some work there. Now the message has to come back to the task tracker saying this is the task you need to execute. If the files that are needed to execute that task, the jar, the job.xml, the job.scripts, whatever you have, if those are not already present on the task tracker, then it has to go to the HDFS, it has to fetch all those files, localize them, and now it has to start the task which is running as a separate JVM, right? It has to fork off a process. That process has to execute the user code. So all that takes a few seconds at least, right? Or a few hundreds of milliseconds. So if you have just this overhead, the fixed cost that is associated with the task launching to be a few seconds, then how can you how can you scale your application if the entire task is going to finish in another 2 or 3 seconds, right? So there is one way to control how much time a task actually takes, which is how much input it consumes. Okay? So if you have, let's say, 100 million files of 1 megabyte each, and you are going to launch 100 million tasks where each task finishes processing this 1 megabyte file in a second, obviously that is not going to scale. But if you have, let's say, 10 tasks, and then each of these tasks works on a several million bytes, right? And then that means each task is going to take a few tenths of seconds. Then you will be able to amortize this task launching over it, right? So for increasing task granularity, you have to combine. You should combine multiple small files into large ones, right? Maximize the split sizes. If you are using 32 megabyte block size, go to 64, go to 128 megabyte, go to 512. 5 years ago when we started a Hadoop cluster, we basically made this, at Yahoo, we made this choice of keeping the block size, GFS block size, which essentially corresponds to a split size in MapReduce framework, to 128 megabytes. Now, 5 years later, the CPUs are much faster. We have much larger memory in each of these boxes, okay? And it's still at 128 megabytes. Now, you need your applications to be agile enough to process or to work on block sizes which are not 128 megabytes. So that's something that we need to work on. Is as a Hadoop community, we basically need to program your applications so that they can actually deal without rewriting the code. They can actually deal with these larger block sizes. All right. So having said all that, basically let's just distill that down into a few bullet points as to what we should be doing, right, while writing scalable Hadoop applications. So first thing might seem very counterintuitive because we are all in the business of extracting the last bound from the CPUs, and higher level languages like Pig or Hive obviously add some more overhead on your processing, right? But the good thing is that the Pig development team is really smart here at Yahoo and elsewhere, right? And so they are going to be optimizing more and more the Pig language, the way it basically gets interpreted on the Hadoop side. And without rewriting any of your code, you just get the benefits of their work, right? So use higher level languages as much as possible, right? If you have multiple small files, polish them into larger ones. Use bigger HDFS block size. On the map side, basically all the map output gets into the in-memory buffers before the buffer fills up, and now it has to be written outside on the disk, and then so that the map task can continue computation, right? So tune the buffer sizes because disks are slow, right? However fast they may go, they will still be slower than the CPU processing speeds or memory access speeds, okay? So tune those buffer sizes so that you don't have to spill very often to the disk, okay? The capacity scheduler, if you use them in your deployment, it allows you to consume more than one slot per task. So you can ask the Hadoop scheduler, the capacity scheduler, to say, I actually need more than 512 megabytes of memory, and therefore I will like to wait until 2 task slots become free so that I can launch my task here. Okay? Try to avoid that, because what happens is that the task requests 2 slots. It gets 1 slot, it blocks it until the second slot on the same machine becomes available. That you are going to ruin the utilization of your cluster because of that. Okay? I've already talked about the combiners. Use compression anywhere, everywhere. Okay? The compression, the general guideline is that the compression algorithm that you choose, and Hadoop allows you very simply to specify different compression algorithms, the LZO, gzip, bzip2, whatever you have. Okay? It should be CPU efficient for the intermediate data. What happens is that the map task is compressing the output, and while other map tasks on the same machine are running simultaneously. So you should not take up inordinate number of CPU for otherwise other map tasks on the same machine will suffer. Okay? So for intermediate data, it should be CPU efficient. LZO works very well in that case. Okay? But when you write the output data, since you are typically writing in replication of tree, the same message is getting retransmitted and hopping on the network at least twice. Okay? So make sure, and then getting returned to 3 disks. So make sure that your output data compression that you use is disk efficient, that is reduces the size a lot, and gzip and bzip2 come to mind. Those are the most commonly used. We haven't talked about distributed cache much, but distributed cache is a mechanism in Hadoop to distribute the side files other than the primary input. Okay? So if your side files themselves are in gigabytes, whereas your map input you are going to process only, let's say, 128 megabytes, there won't be any scaling in your application. I can guarantee you that. Okay, so make sure that when only the small files are the ones that actually get distributed via distributed cache. If you are using some sort of state sharing mechanism and outside of the regular MapReduce framework by making a call directly to the job tracker or to the name node from each task, please try to avoid that because those are currently the single node bottlenecks that you have in your 1000 node clusters. Okay. So with those best practices, I will take questions. So the question is there any benefit in using a shared storage in your HDFS or as part of secondary? Right. Right. It will definitely reduce the latency. I believe the fiber channel latency is of the order of tens of microseconds rather than 300 microseconds. It will definitely help. The kind of applications that we used to work with at Yahoo basically dealt with really large data sets. So essentially it was limited by bandwidth more than by latency. But then, so we had to tune the number of reduced tasks, for example, in order to optimize that. If you are using Hive, what is the best way to decide number of producers or specify number of producers? Because specification can be done with this select /star parallel, etc. Right? So how do you determine the number of producers? So the best way to do it is to see what constructs. I mean, this is you have to think like a Hive compiler, right? What constructs are going to induce a reduced task? If you have just a select from there, it's not going to have any reduced task, right? It's basically just projections. That's pretty much it, or filtering, right? But if you have something that induces join across multiple tables, most likely, I mean, depending on this data sizes, Hive apparently has become much more intelligent now to push joins to the map side. But if, let's say, your two data sets that you are trying to join is of almost equal size or comparable size, then the join happens on the reduced side. Now you got to say, so if you have A join B, then it's going to, the size A plus size B is what is going to get shuffled and is going to get to the reducers finally, right? So you got to basically decide. So one of the ballpark numbers that we had come up with is each of your reducers should take, and this was very highly dependent on the configuration that we had at Yahoo at that time, is each of your reducers should have about 1 to 2 gigabytes of input. Okay? So based on that, now you determine your number of reducers, and that's how you specify your parallel data.
When you have data schemas, especially with respect to the number of reducers, is there anything in the infrastructure that can have some mechanism to understand what's the data schema and then moderately dynamically choose the number of reducers?
Yeah, so the question is if you have skew in your data, which is very common, right? Is there any way in the infrastructure to do automatic sampling and determining the number of reducers? It's not only the number of reducers. You have to, when you have skew in your data, you typically have to override the partitioner itself. Because when you have skew in your data and you basically, let's say, have one key that occurs 90% of the time, and since the partitioning decision is based only on the key, that record or those 90% of the records are going to go to one reducer, no matter how many reducers you have in your application, right? So you got to change your partitioner in some way. Now your partitioner has to take into account not only the key, but value as well. And you will typically find that when you combine key with value, your skew goes away, right? And in that case, then obviously this changes your algorithm also a little bit. So you got to really think about that. So there is no silver bullet for solving the data stream. What Pig does, for example, that I know, and probably Hive also has a sampling partitioner, is Pig, whenever you have an order by or something like that, you basically have a separate MapReduce job which does the sampling, stores that sample as an HDFS file, and takes that sample in the next map input format to, in the partitioner to actually decide on the partitioning scheme. Right? So Pig already does that well. Obviously, the sampling partitioner is based on assuming that the input has some distribution, right? And if that distribution does not match, there will be glitches, right? Yeah, that's the way of that.